GATE 2024 thermodynamic questions. In an AB solid solution, the activity and the mole fraction of A are given by A and XA, then the activity coefficient is given by, A is equal to uh, gamma A into XA. So activity coefficient is nothing but AA by XA. Okay. Which one of the following is equilibrium associated with constant pressure and temperature? Uh, you know, the the Gibbs free energy dg is equal to vdp minus sdt. So it depends on both temperature and pressure. So if you want to make the thermodynamics and equilibrium for an isolated system held at constant temperature and pressure, we need both entropy maximization in order to increase more negative value, and then this gives more negative delta G value, because more is a delta G, more is feasible is a reaction. So we need minimization of delta G and maximization of entropy. This value should be negligible. So we should make this as more negative as possible. So increase this value, delta S value and delta G value. So it is minimization of Gibbs free energy and entropy maximization. In other words, the system reaches equilibrium if its Gibbs free energy is its lowest possible value. So the system is stable and reached a balanced state. When Gibbs free energy is minimized, the system has achieved the most favorable balance between energy and entropy. An ideal solution of 10 grams and 50 grams B at the 673 Kelvin, the molar free energy of mixing is given by delta G mixing equal to RT XA ln XA plus XB ln XB, which is given by 8.314 into temperature is given as 673 Kelvin. And if you'll see XA, it is 10 by 10 plus 50. So it is 1 by 6. And XB is 50 by 10 plus 50 is equal to 5 by 6. So it is 1 by 6 ln 1 by 6 plus 5 by 6 ln 5 by 6. So this is equal to minus 3.01 kilojoule per mole. And we check the values asked in kilojoule per mole. So it is minus 3.01. Coming to corrosion, GATE 2024 corrosion questions. It's a very good question. It's a very good conceptual question. So if you'll see the microstructure of a quenched steel tempered at a temperature T1 less than T2 less than T3 for a fixed time and schematically illustrated. The solid circle represents cemented particles in ferrite matrix R1 bar, R2 bar, and R3 bar, and the average radius of the cemented particles V1, V2, and V3 at the temperature T1, T2, and T3. It's given R1 bar is less than, R2 bar is less than, R3 bar, and V1 is less than, V2 is equal. The cementite of the steel is more noble than ferrite. Which one of the following three microstructure have highest corrosion rate when exposed to 3.58%? So now you need to see whether the factors which affect the corrosion rate. The surface area of the exposed cementite, the more is the cementite surface area, the gradually leads to high corrosion rate. The galvanic coupling between the cementite and ferrite, since cementite is more noble than ferrite, it acts as cathode in galvanic cell. This accelerates the corrosion of the surrounding ferrite. So therefore, this is ferrite and this is cementite. If it is very small, uh, this causes corrosion, but This does not affect much. The corrosion rate of steel microstructure when exposed to aqueous NaCl can be influenced by various factors, including volume fraction, size of the cementite, and in this scenario, the the volume fraction and the size of cemented particle, uh, the cementite of steel is more noble than ferrite. So when exposed to aqueous corrosion, the presence of cemented particle can accelerate the corrosion process due to galvanic coupling. The galvanic corrosion occurs when two dissimilar metals are in contact with electrolyte, leading to corrosion of less noble metal and protects the more noble metal. That is cathode. Less noble is anode. So if you'll see, uh, this is R1 and this is R2. Here it is given volume of V2 is given equal to volume of V3. So 1, 2, 3, 4, 5, 6. So 6 into 4 pi by 3 into R2 cube is equal to 2 into 4 pi by 3 R3 cube. So this gets cancelled. This is 3. So R3 cube is equal to R2 cube into 3. So let's take R2 as 1. So R3 is equal to 3 power 1 by 3, right? R that's 3 power 1 by 3. Now, you need to see more is the surface area, lesser will be the corrosion. So, which has the more corrosion, which has more surface area, we need to see. So, 4 pi R square into 6, and it is 2 into 4 pi R3 square. 6 into 4 pi into R2 square, if you'll see, if you take 1, this is 24 pi, and this is equal to 8 pi into 3 power 2 by 3. So what is this value? Let's check it. So if you'll see, the if you'll see, this is 24 into 3.14, which is 75.36. And this is 8 into 3.14 into 3 power 0.67, which is 52.44. If you'll see in third case, anyhow, the cementite acts as cathode here. Fe3C is cathode and anode is alpha. So alpha should be as high as possible to decrease, because whenever the first material which corrodes is anode itself. So anode should be as large as possible in order to reduce the there should not be a significant area relation between anode and cathode. Should be very large difference. But here if you'll see, anode should be very large. But here if you'll see, the area is 75.36 for the cathode, and compared to R2, compared to T2, T3 having lesser surface area for the corrosion to happen. So microstructure of T2 will be corroding faster. Two cupric ion concentration in the electrolyte at 298 Kelvin required to make a potential of pure copper at 0 point equal to 0.17 volt, and is 10 power dash into 10 power minus 6 gram mole per liter. Given Faraday law constant and the gas constant, standard reduction of the copper is given as E naught is equal to 0.34. So, according to the Nernst equation, E is equal to E naught minus RT by NF ln Q, where Q is product concentration by reactant concentration. So, here it is Cu plus 2 is converting to the cupric ion concentration in an electrolyte is required to make pure copper. So, it is product concentration is Cu by Cu plus 2. The activity this can be considered as 1. So it is E is equal to uh, standard reduction potential is 0.34, and this is given as 0.17 minus RT by 2F ln 1 by copper concentration So it is given as, uh, if you calculate, you'll get concentration equal to 0.37. It is minus 0.17. So into 2 into r square. So you'll get 1.77 into 10 power minus 6. So copper concentration is 1.77. Okay. The mild steel pipeline is connected to a zinc cathode for cathode protection at a current density of 10 milliampere per meter square. The quantity of the zinc required per square meter of the pipeline per year is dash. Here, if you'll see, you know, the current density is given as, current density I is given as 10 milliampere per meter square, which is equivalent to 0.01 ampere per meter square. You know, the charge, the quantity required, W is equal to, remember W is equal to ZIT, where Z is the equivalent, atomic equivalent, and which is equal to molecular weight by N valency I into, so it is IT can be written as Q by F, which is E by F. Then Q is IT. Then you get 90, 96,500, and it is 0.01 into, time is for 1 year. It is 365 into 24 into 60 into 60, which is equal to, M is given as the 65, and this is 2. So you'll get 65 into Q is 315, 315, 360 by 2 into 96,500 is 19,000, 1,92,000, which is equal to 106.5 grams. So weight is 106 grams per meter square per year. Thank you.